In this new unit, we're going to be focusing on a concept, a very important concept in general chemistry called stoichiometry. And this is just, it's kind of a big fancy word for basically really how we can relate the mass of reactants to mass of products. Or say, for example, we want to make a certain amount of a compound. How much or how much mass do we need of the reactants in order to make that target amount? And the best way to really relate stoichiometry to something real world is through cooking. You might ask, how is that even relevant? Well, I look at the kitchen as a lab. It's just I get to eat the products once I'm done with them. And so let's take just kind of a simple recipe and put it into chemistry terms. We could take, say, a cup of pancake mix and add 3/4 cup of milk and then 1 egg. Mix it all up in a quote unquote chemical reaction, and that'll make some pancakes. We'll say 8 pancakes. Now, what I want you to do is look at these numbers here as the coefficients, or we call them stoichiometric coefficients. And this basically says that in order to make 8 pancakes, I need 1 cup of mix, 3/4 cup of milk, and 1 egg. Now, let's say I have people coming over for breakfast, and now all of a sudden, I need to make 24 pancakes. So, how many eggs do I need to make 24 pancakes? Now, that's something we can kind of do in our head. We just are like, well, that's 3 times as many pancakes, so I need 3 times as many eggs. But here's the important thing I want to show you how you use these coefficients from the balanced equation. You use them as conversion factors. Because if I want to make 24 pancakes, the balanced equation says, well, in order to make 8 pancakes, I need 1 egg. Notice here I've set this up just like a conversion, and these units cancel out. And this comes out to what we had, done in our head. We need 3 eggs. So what does all of this have to do with actual, chemical reactions we're going to do in the lab? It's the same exact concept. Let's say we are going to take hydrogen and oxygen and combine them to make water. Hmm. Now, the first and most important thing before you do anything is make sure you have a balanced equation. And that's something we learned how to do in the previous unit. Now, sometimes the equation might be balanced for you. Sometimes you might have to do that. So just be aware that that's the first thing. So let's say I want to do a chemical reaction where I need 11 moles of water. How many moles of hydrogen and oxygen do I need to use? So let's again analyze what these um, coefficients mean. And let's just, we assume the one or that oxygen is one. Let's figure out what those mean. Okay, we can go down to very, very small number, smallest factor and say, well, 2 molecules of hydrogen will react with 1 molecule of oxygen to make 2 molecules of water. But very rarely do we work on that scale. And so we expand it to basically say 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. And we're going to use those coefficients as our conversion factors to answer this problem. We start with what we're given. We need to make 11 moles of water. So how much hydrogen is that going to require? Well, the conversion factor says 2 moles of water comes from 2 moles of hydrogen. Again, where am I getting these twos from? The balanced equation. So moles of water cancel out. You know, if you wanted to, you could cancel out the 2 and the 2, but that comes out to 11 moles of hydrogen are needed. Now let's do the same thing for oxygen. Again, we're starting with 11 moles of water. How much oxygen do I need? Well, I'm going to use the coefficients from the balanced equation. The equation says 2 moles of water comes from 1 mole of oxygen. And so the units cancel out, and we're just up with moles of oxygen. So we'll need 5.5 moles of O2 in order to do this reaction, in order to get the amount that we're going to make. In a little bit, we'll talk about like what happens if we don't have that specific amount. What happens if we have less? We'll get to that in the next set of lectures. But the important thing that you need to develop, the important skill, is you need to get good at getting to moles. That means at bare minimum, you need to be able to go from grams to moles using the molar mass. Well, we're going to take it deeper though, and we're going to look at um, um, concentration. So using molarity within stoichiometry, we'll look at mass percent, we'll look at density, and how all of those things can help us get to moles. So let's do a little bit more practice with this. So how many moles of N2 and H2 are required to make 8 moles of NH3? So here's the balanced equation for this. And so we need to know how many moles of our reactants do we need in order to make 8 moles of ammonia. So that's where we're going to start. Start with 8 moles of ammonia. And we're going to set up a conversion factor where we use the coefficients from the balanced equation. 2 moles of ammonia, and let's just start with nitrogen, requires 1 mole of nitrogen based on the balanced equation. So again, where am I getting these numbers from? Here's the 2 and the 2. And then since that is blank there, we understand it to be 1. And that comes out to 4 moles. I guess I should keep track of good sig figs. 8.00 moles of N2 are needed. Now, while I'm talking about sig figs, one thing to note is that those coefficients from the balanced equation have an infinite number. That's an exact number. So these have an infinite number of significant figures. Now let's do the same thing for hydrogen. So I need to make 8 moles of ammonia. The unit I want to cancel out goes on the bottom. So the coefficient is 2. So 2 moles of ammonia. And the balanced equation says I need 3 moles of hydrogen in order to accomplish this. So all of that cancels out. Plug it into my equation, or plug it in my calculator, sorry. And I get 12 moles of H2 needed. All right, let's do this same thing for the next one. So let me draw out the equation here. Okay, so here's our balanced equation to react um, sulfur dioxide and oxygen with water to make sulfuric acid. Now, notice here that it's not asking us about sulfuric acid. It's asking us how much of these two reactants do we need in order to fully react with 24 moles of water. So it's like a recipe. You want to make sure you have enough of every single ingredient, or else you're not going to get the amount of product, the amount of food that you wanted to set out to make. So if I'm starting with 24 moles of water, I need to figure out how much SO2 and oxygen will fully react with that 24 moles of water. So I'm going to start with what I'm given and use the coefficients from the balanced equation to figure out how much I need of each other reactant. So the equation says 2 moles of water will react with 2 moles of SO2. So that comes out to 24 moles of SO2. Now, how about oxygen? All right, again, I'll start from the same place. 24 moles of water. The balanced equation says 2 moles of water requires 1 mole of oxygen. And so I'll need 12 moles of oxygen in order to do this reaction completely. All right, and let's look at one more. This one, the numbers won't be so nice and round, which is pretty much going to happen like 99% of the time. You're going to have more complex numbers than stuff you can do in your head. So let's look at, here's our equation for this reaction. We're going to react aluminum with iodine to make aluminum triiodide. And there's our balanced equation. So the first question asks us if we have 0.429 moles of aluminum, how much iodine do I need to do this reaction? And then how much product am I going to get? So let's just answer the iodine question first. I start with what I'm given, 0.429 moles of aluminum, and then I use the coefficients from the balanced equation. This says that 2 moles of aluminum is required to react with 3 moles of iodine. So moles of aluminum cancels out. I'm left with moles of iodine. So I need 0.644 moles of aluminum. Now, how much of the product is this going to make? Now, in theory, I could use either number because now I know, oops, I should say iodine. I know how many moles of iodine it requires. So I could start with either the 0.429 or I could start with the iodine. So it doesn't matter which one I start with. I'll just keep it consistent and start with the moles of aluminum. But I encourage you, try this calculation by starting with the iodine and figure out how much product you'll get. And you'll end up with the same exact answer. Now again, I'm going to use the coefficients from the balanced equation. 2 moles of aluminum will make 2 moles of aluminum triiodide. Moles cancel out. I can cancel out the 2 and the 2 if you want. And so we get 0.429 moles of aluminum triiodide. Now to kind of round out this video, I want to show you where we're going. The key thing that you have to be able to do is to get to moles, no matter what information you're given. Because if you have a reaction, we're going to go from A to B. If you know how many moles of A you're starting with, you can easily figure out how many moles of B you're going to make. And we could take that a step further because right now we've just been talking about moles. But what if you wanted to know, and this is a lot more common, what if you wanted to know how much, what the mass of how much you can make? Well, you can get from moles to mass by using the molar mass. In contrast, what if in the problem I say that you start off with a certain number of grams of a reactant? So if you're starting here, you can get to moles by using the molar mass. Well, what if we're doing the reaction in solutions? And I tell you that, well, you're starting with a certain volume of a solution of a reactant, and I give you the concentration. Well, that's another way you can get to moles. Or like if you have moles of your product and you want to know what the new concentration of the solution is, you can use volume or molarity. So the key thing here with this first day of lectures is being able to go in between all of these things and get ultimately to moles first. Once you get there first, then the rest of it is fairly straightforward.